Hello students. So how are you feeling today? Hope you are feeling all energetic and excited and studying chemistry well, preparing for your exam. And in that context, you must have tried to solve the specimen paper which was given by the Cambridge board in 2022. And I have solved some questions from the specimen paper which are available in the playlist. And now the two questions which I had not solved, question number 5 and question number 6. These are the two questions I'm going to solve. I've already written down the answers, so I will be able to cover these two questions really fast and it will save your time. So let's go ahead and hope you will watch the video till the end. So the first question is, lattice energies are always negative, showing that they represent exothermic changes. Explain what is meant by lattice energy. So this is a very simple question. When 1 mole of an ionic compound is formed from gaseous ions under standard conditions, that is called as the lattice energy. As you know, for example, if you have to form 1 mole of sodium chloride, right, then you would be taking the sodium ions in the gaseous state and they would be combining with the chloride ions in the gaseous state to form 1 mole of the ionic solid. The energy change during that process is known as the lattice energy. Okay, so why lattice energy is an exothermic process? Because all bond formations are exothermic. So here ionic bonds are formed and therefore it is an exothermic process. Now we go to this question which is based on the lattice energy, and we have to find the lattice energy of potassium oxide based on the following data. And I have made the cycle, the enthalpy cycle, to help you solve this problem. And since we have to find the lattice energy, so when the potassium ions combine with the oxide ions to form potassium oxide, that's the lattice energy. That is what we have to find. And we also have the data of the enthalpy of formation from potassium and oxygen, and then rest of the cycle you have to complete. For completion, you can take the information from the table. So you can say that first we change potassium solid to potassium gas. That is the enthalpy of atomization for 2 moles. It's 2 times 89. And then we ionize 2 moles of potassium. So we take this value, 418. And then we have to atomize oxygen gas, half mole. So we take half of this 496, and then we need 2 electron affinities for oxygen because we have to form O2 minus. So we take these two values, minus 141 and 798. And after doing this, we can easily say that this minus 361 will be equal to sum of all this. And when we put this in the equation, we are able to get the value for the lattice energy, which turns out to be minus 2280. If you have not understood, you can stop this video and you can see each step, and then you can see how the values have been put. And then we have to say that the lattice energy of sodium oxide differs from the lattice energy of potassium oxide. So we have to tick under the correct column. So it's more negative. Reason is that the sodium ion is smaller than the potassium ion, because sodium is in the second period and potassium is in the third period. So when the ions are smaller, they have stronger forces of attraction, and therefore there is a greater exothermic reaction. Alright, so that completes question number 5. Now we go to question number 6, which is about the transition element. So what is a transition element? So transition element, obviously you know that they are in the D block, but there is one more condition that when they form a stable ion, then it should have an incomplete D subshell. That means it should not be D10 or D0, it should be anywhere between 1 and 9. So that's the definition. Now what is a monodentate ligand? Obviously it forms one dative bond and it has one lone pair of electrons. So a molecular ion that chooses one lone pair of electrons to form a dative bond to a metal atom or an ion is a monodentate ligand. So we have bidentate, multidentate ligands also. Okay, now the aqueous silver ions react with ammonia to form a linear complex. So since it is linear, so I think you can understand that you know, there should be right, it should be linear, means you should have ammonia on both the sides like this, right? That obviously means that we need two ammonia, right? So it will form the dative bonds like this, right? So it would be linear, and then this is the complex ion, and because silver has this +1 charge, so we'll have a +1 charge here. Ammonia molecules don't have any charge, so this will be +1. So I think this is the formula of the complex. Okay. Now there are two isomeric complex ions with the formula this. One is green and the other is violet. Suggests the type of isomerism. Now here there is a confusion in the minds of the students because they don't know how to find that, whether it will be geometrical isomerism or it will be optical isomerism. So for that I will give you a clue that if it has to be optical isomerism, then these ligands should be bidentate or multidentate. Whereas here the ligands are monodentate, and in the case of monodentate ligands we don't have optical isomerism. So that gives you the clue that optical isomerism is ruled out, so it will be geometrical isomerism. And the two chlorines, we have to see with respect to the chlorine, not with respect to ammonia, because there are two chlorines. So either the two chlorines can form an angle of 180 degree up and down this plane, or this may be in the plane and this chlorine is projecting upwards, making an angle of 90 degree. So this is the cis and the previous one is the trans isomer. Now let me also tell you that it really does not matter that whether the chlorine is here or whether the chlorine is here or whether the chlorine is here or whether the chlorine is here. All these four positions are equivalent and all represent the cis isomer. Okay, and in place of this chlorine, actually you can draw the chlorine here also, right? So please don't be confused that this is the only correct representation. It can be any other representation as well. Okay, so now why they have different colors? This is obviously you have studied under the transition elements that the d block elements have degenerate d orbitals, meaning having the same energy, but when they form the complex ions and when they combine with ligands, then these the 5 orbitals now are divided into 2 energy levels. 3 of them are at the lower energy level and 2 of them are at a little higher energy level. Now this energy difference can vary, it can be less or more depending upon the nature of the ligands and the nature of the metal ion or the atom. And when the visible light falls on the complex, then a suitable wavelength is absorbed by the complex, which promotes the electron from the lower level to the higher level, and then the transmitted light gives rise to the color, and this transmitted light is complementary to the color which has been absorbed. And because this will be different for the two complexes, therefore these two complexes will show different colors. There is no way to find out unless you do the calculations of the energy levels that what color those compounds will have, whether they'll be green, yellow, blue. That you cannot find out unless you do the calculations. So you don't have to do that. You have to memorize or learn wherever required that what would be the colors of the complexes. Okay, then we go to this. We have to draw the three-dimensional diagrams. See, here there is optical isomerism, and you can see that these are the bidentate ligands. So as I told short time back, that if they were the monodentate ligands, then you would not have the optical isomerism. So here optical isomerism is possible because they are bidentate ligands, and you can draw the octahedral complex such that the nitrogens occupy all the 6 positions in this complex, and then you can draw its mirror image, and that will be the correct answer. These wavy lines represent the bonds going backwards, and these thick wedges represent the bonds coming forward, and these two vertical lines are above and below the plane. Then why does this 1,2-diamine ethane, why is it a Lowry-Bronsted base? Because it has a lone pair of electrons, and therefore it is a proton acceptor. That's a definition of a base, and that's why ethane 1,2-diamine acts as a Lowry-Bronsted base. Now because it's a base, it can react with hydrochloric acid, any acid, and the NH2 groups can get protonated. They will become NH3 plus, NH3 plus, and then they will be surrounded by the negatively charged chloride ions forming ionic bond, and therefore this will be the equation for the reaction of ethane 1,2-diamine with 2 moles of hydrochloric acid. In this case, you have to draw the structure of the polymer showing 2 repeat units of 1,2-diamine, this one, and ethane dioic acid, this one. So you know that the carboxyl group and the NH2 group, when they interact, they can form the peptide bond CONH, and water molecule can be removed, and a condensation reaction takes place. Since you have to form 2 repeat units, and 1 repeat unit contains 2 molecules, so obviously there is going to be 4 molecules in the answer, and that you can see here that there are 2 molecules of the acid and 2 molecules of the amine, which form the 2 repeat units, and there is a zigzag carbon skeleton, and the NH groups face up and down. So this is how you will draw the repeat unit for the polymer, and that actually completes your 2 questions, 5 and 6 of the specimen paper. As I said, we completed in a record time because all the answers were already written, and it saved me a lot of time, and I could just focus on the explanation. If you like the video, please give it a like and share it with your friends, and thanks a lot for watching.